there's actually more people than this enrolled in the class, so I don't know where they're at. But, so welcome to ME6194. So Science and Engineering Foundations of Additive Manufacturing. Today's class is pretty much going to be an intro to the class. I may get into the first module, or I guess we'll end up being the second module of the course. We'll see how this goes, but I wanted to give you kind of an introduction to the course, what the expectations are, why this course may be a little bit different than other courses you may have taken before. So first off, I'll just introduce myself, and then I'll actually have everyone go around and introduce themselves as well, because I'm interested to see, one, why you're in this class. Because I think this is a pretty specialized class. And so I'm interested to see if you guys are, what type of research you may be performing, et cetera. So first off, myself, as an introduction, my name is Professor David Helsley. If you want to, I don't know if it's, the right word is accurate, it's probably inaccurate. If you want to accurately say my last name as it was butchered once my ancestors got to Ellis Island, it would be Helsley. The proper Germanic form is probably something I can't pronounce. But I go by Professor Helsley, so like Helsley. But I've had this funny name my whole life, so I don't get offended if it's mispronounced. So kind of background, I've been at Ohio State for 2 years. My training, I did my actually undergraduate degree in this department, mechanical engineering, at Ohio State, graduated in 2005. Then went and did my master's and PhD at University of Illinois, where I looked at control of additive manufacturing processes, specifically what we'll call material extrusion processes in this course. Then I did a postdoc at UCLA, and in terms of my background is fundamentally in control systems. So at the undergraduate level, I teach a control systems course. I also teach a robotics course at the graduate level. And so my specialty is in the control of additive manufacturing processes. My specialty is not in additive manufacturing in general. I'll talk a little bit about what that means for this course as well as I get into the kind of that content. But my background is mostly in additive manufacturing and control of that. And I just wanted to really quickly go through some things I've worked on here. So I'll pass around some artifacts, and we'll have a chance to look at these artifacts more in the future. The first one you'll barely be able to see, especially people towards the front where the light's out, so you may not be able to see it at all. But if you look, okay, so there are words on the back of this. If you have the words, you can read them, so they're upright. And you look at the upper left corner, you'll see some very, very small features that we've created. So one thing that we look at is we look at material jetting additive manufacturing processes in my lab. So these are processes that are like inkjet printing. So you've seen inkjet printers, of course, in whatever your house, etc. And those make features on the order of around 30 to 100 microns in their features. So we look at additive manufacturing processes for the production of electronics, microfluidic devices, where we have features on the order of 1 micron. Right, so that's somewhere around less than 1/20th the width of a human hair is what we fabricate. And so if you look in the very small regions of the silicon wafer, you can see some of the things that we've made, and that's what we look at controlling. So this would be a microscale additive manufacturing process. This is an example of a microfluidic device that we've made, and using some of the principles of additive manufacturing, be able to put different materials in different locations to build up three-dimensional structures. That's one thing we've done at the micro scale. You probably can't, you're not seeing my cursor, are you? All right, I gotta move over here. So let me change, actually. Display settings. This is duplicate. It's for some reason automatically going into presenter mode. Okay. from current slide. There we go. Okay. All right, so this would be the micro scale things I've worked at. I've also looked at slightly larger scale. So those of you who have seen MakerBots, this is a tool that I've used that's fairly similar to MakerBots. It's actually all at room temperature, so it doesn't melt the material. But we've looked at making synthetic bioscaffolds with this. I don't have an artifact here to show you. And then another thing I've looked at is something called powder bed fusion, which we'll talk about probably the most in this class because it's becoming one of the more popular additive manufacturing technologies, which this video will show the basic idea, but you have a bed of powder, and at each layer you take a laser and you scan the surface and you melt the powder selectively in that region to then build up structures layer by layer. So once you melt, you can see my cursor now, right? Okay, so once you melt that region, then you use a recoater blade to then put more powder here, and then you build this up in a layer by layer fashion. So what you'll see, I'll pass this around. Oops. I'll pass this around. This is a project where we looked at how do you make, this is made of 316L stainless steel. And this is something that we looked at, basically the physics of making these processes, or making these parts, and basically distortion of this part as we print. That's something that we'll talk about extensively in this class, how if you have basically a very thermally driven process, how that causes distortion in the part you're making. But what you see here in this picture is this part that's being passed around, this is when it was still on the build plate, and then this is now taken off the build plate. So that's a little bit of background about myself. I did want to go around the room, and one thing I'm interested in is what your background is. So please tell me what you got your degree in undergraduate. If you're still an undergraduate, please let me know that as well. And then I guess I want to know why you are here too, because this is a pretty specific class. So I'm interested to know, are you doing additive manufacturing research? Are you planning to do additive manufacturing research? Are you just generally interested in additive manufacturing? Because one of the opportunities that we have with a very small class is I get to potentially tailor the class a little bit to what the students want to see, right? So I guess we'll start up in the front here.
Yes, I'm Andrew. I'm undergrad. I joined this class. AM seems like a cool learning field, so I just wanted to learn more about it, essentially.
Yeah, so undergrad in mechanical engineering, right?
I'm Ryan. I'm a master's student. I got my undergrad in mechanical engineering. I'm taking this course because you're starting to see AM processes a lot in industry, and I thought I was learning as much as I could about it before I get into industry.
Okay, you're Ryan Brady? Is that, sorry,
Ryan
the two Ryans. Okay, great. Okay. Okay, so Dr. DePino's up? Okay.
Ryan Brady, the other Ryan, I guess.
Yeah.
So I got my undergrad degree in aeronautical engineering. I actually currently work for GE Aviation, currently GE's program to get my master's. We actually use quite a bit of this additive manufacturing technology right now. So I guess just generally interested in a little bit more about the process and science behind it.
Okay.
I'm in fact,
Sorry, yeah, everyone's got to speak up as these air conditioners are really loud.
Yeah, I'm dance singer. I'm a master's student.
Okay.
So I'm interested in additive manufacturing as it is a budding field and it has a lot of opportunity. So I want to do science.
Okay. Have you registered for the class?
I think I was having some problems, so Nick might register me.
Okay. All right, so we'll have one more, because right now we have currently 9 people enrolled, so I guess that'll make 10. Okay? All right.
Hi everyone, I'm Tanmay Gupta. I work with, I'm a master's student in mechanical engineering, and I work with Professor Alton in sheet metal forming. So
Okay.
it's kind of manufacturing, so I just wanted to learn what's new in manufacturing.
Okay, so you work in general manufacturing, but you're interested in
my research areas in sheet metal forming straight back in sheet metal forming. So,
Okay.
Kevin Spicer, graduate student in ME. Just interest in additive manufacturing. So it's definitely an emerging field. I'm noticing a lot with some internships they're using a lot of this type of stuff.
Okay, you said master students or PhD?
Masters.
Masters. Mechanical, okay.
I'm Prashant Raghavan. I'm a postdoctoral researcher in mechanical engineering. I got my bachelor's and master's in chemical engineering and a PhD in mechanical engineering. We're looking into modifying auto heads to 3D print structural composites. So that's pretty much why I'm here.
I'm Nathaniel Wood. I'm a PhD student in mechanical engineering. I pursue research in additive manufacturing.
I'm AJ. I'm an undergraduate. I'm probably not registered to the class yet because there's a few more paperwork to fill out. I'm interested in additive manufacturing because I do 3D printing for my research in chemical engineering for nuclear resistant plastics, and my advisor will be next class.
Okay. You're the Dr. Brunelli's student. Yeah. Okay.
I'm Yusuf Ron, and PhD student. I'm in mechanical engineering and now working for the professor Additive. So I'm here want to know more fundamentals of the additive manufacturing.
Okay.
I'm Dan. I'm a student. I'm working for
Good on you. Okay, all of the Pino students working in ultrasonic AM? Okay. 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 I know nothing about ultrasonic AM, so it's a very diverse field. Okay, so thanks for all that. I guess it gives me a little better sense of what your backgrounds are. How many of you, is this your first graduate class? Okay, so 5 students. Okay. So, sorry, Ryan, right? You worked in industry for a little while?
So I'm actually still working in industry.
Okay, yeah, okay. You're taking kind of a leave to do this.
Yes, I've been in GE for 3 years now, taking the most special leave in November.
Okay, is everyone else coming straight to graduate school? No industry? Okay. So I guess I want to talk a little bit about a philosophy of a graduate class. For those of you who've already taken graduate classes, you may agree with me, you may not, but here's how I handle it. This is a small graduate class. If everyone is doing the work and really understanding the material, I have no problem with giving everyone in the class an A. Right? Now that's the caveat of everyone doing their work and understanding the material. It's not like an undergraduate class where we're shooting for some sort of undergraduate, so average GPA in the course. Okay, so because of that, there's a little bit different focus in what we are going to look at here. I think as a graduate student, you should be more focused on how do I understand the material as best possible to then help you with your research projects that you're doing. Either whether or not that be using this as R&D in industry or in your research project in your actual lab here. Okay, so we're going to spend, and I'll go through the syllabus and how that's reflected in the syllabus. We're actually spend a lot of time looking at old journal articles and also some recent journal articles. The one I passed out today, you notice, you may have seen the date on that, 1940 something, I forget, is the date of that journal article. We're going to be going through a lot of journal articles, more focusing on understanding the principles of what we're talking about, et cetera, and not so much on a lot of work. And I'll get into the syllabus part of this, but there's not a ton of work, but when you are working, you're expected to understand the material at a pretty high level, which is going to take more time. It's not going to be, you're not going to be able to basically cram and get through a homework assignment in the night before it's due, but they're not going to be homework assignments due every day, or every week, I mean, for an undergraduate class. So there's a little bit different focus. So for those of you not taking a graduate class, I guess we'll ease into getting used to that focus, but we're mostly focusing on your understanding of the material. Some logistics for this course. Office hours have yet to be set, so I like to just put this up to a poll. So I'll send out an email this afternoon to everyone in the class. For those of you who are not currently registered in the class or will not be registering for the class because you're auditing, please send me an email just so I have your contact information. And then I'll make sure that you're included in this poll. And then I'm just trying to find a time that works for the most amount of people. Yeah. So required literature, there is no book. And I'll talk about this a little bit towards the end because there is not a book that really covers this material. Instead, we're going to be going through a set of journal articles. 2 of them you have in front of you. The rest are still being devised in terms of exactly which ones we're going to look at towards the latter half of the semester. Okay, go. Okay, PowerPoint's freezing. Hi. So we have some handouts going around. And you just missed the interactive part of this. So what's your name, and then why are you taking this class?
My name is Sean Chilati, and I am taking this class because I'm interested in additive manufacturing. My research is in ultrasonic additive manufacturing.
Okay.
So there's some overlap, but I'm interested in it in general.
Okay. So do you work for Dr. DePino? Okay. Okay, PowerPoint decided to close down on me. Okay, how this course will be graded, 20% is class participation. I'll get to this a little bit later on slide 11 here. 40% is going to be 4 homeworks. So like I said, very different from undergraduate class where you usually have somewhere around like a dozen homework sets, right? So it'll just be 4 homeworks, and the last part of this will be a final project. Carmen, I haven't set this up yet. We have like a skeleton. I haven't published it yet. So it's all set up. It just needs to be published. But you'll be using Carmen, and homework and project submissions will all be done on Carmen. So I won't be taking any paper copies of your homework sets. Okay, so that means you can either type out your homework, or you can write it out by hand, and you can scan it, either using the scanners. For those of you who are mechanical engineering students, you can use the scanners in Scott Lab on the 2nd floor. And there are also some cell phone apps that will do this for you now that work pretty well. Schedule. Okay, so this is the basic schedule. I think the main things I want to point out in terms of what would be fixed is when the homeworks are due. When the Carmen site goes live this afternoon, you'll see that there's already a homework assignment published for you to start working on, and that's going to be due September 7th. The final projects are going to be at the end of the semester. There is no final exam. And then journal presentations. Okay, so I'll get to this in a second, but throughout the semester, we're going to, about every 2 weeks, we're going to kind of change it up. And we're going to have a student in the group is going to present a journal article, and then we're going to all discuss that journal article. So you get class participation points. 1 when you give the presentation, that'll be 10 of your 20 points. And so everyone's required to do that once a semester. So when I made this calendar, there are only 7 students enrolled in the class. It looks like we're going to have somewhere around 11 or so, based off who's in here that hasn't signed up yet. And so I'm going to have to fill in a few more blue squares here to fill out the semester. So that's going to change a little bit. But this is the basic schedule for the semester. and course objectives. So this is given in the syllabus. Because this is a graduate class, there's not going to be essentially any focus on this remember part. Okay, so everything you do, whether or not this is homework submissions or this is giving presentations, etc., this can all be prepared in advance, right? There are no tests where you're required to remember something on the spot. And so we're focusing more on the higher levels of Bloom's taxonomy in terms of ideas of understand, apply, analyze, evaluate, and create. Okay, so for me sitting up here lecturing, we're going to be talking about understand, apply, analyze. At the end of the semester, you're going to be required essentially to create something. And I'll get into the two tracks for that in a little bit, but this is just a different focus than what you typically see in an undergraduate class. This I already asked, actually. So we've already said how many are engaged in AM research. But the overall objective of this course, these are specific ones listed on the left. The overall objective here is to prepare you to either perform AM research in your research group here at the university, or to prepare you to perform AM R&D in an industry you may work for. So we have someone who works for GE. Right now, because of billions of dollars of investment, they are kind of leading the field in terms of using AM in their manufacturing workflow, right? And that's in Cincinnati. That's right next door. So in terms of industry opportunities, I think there are going to be even more industry opportunities, and these tools are still in development. It's not like it's sheet metal forming, which has some research groups still looking at it. There's a lot of research still to be done in additive manufacturing. So I think there's quite a lot of opportunity here for things that we do not know. Okay. One thing that I think you should know, because it's going to affect how I present this class, is that there is an online component of this course, and that this is intended to be in conjunction with the Masters of Global Engineering Leadership program. Okay, so you all have probably never heard this before, but you may have noticed that I'm recording this lecture when my PowerPoint went down. So it's just one thing to keep in mind that your voice is being recorded. If that's a problem, please let me know, and I can work with the MGEL program, etc., to work with that situation. So please let me know if that's a problem. Currently, there are 0 online students enrolled in this course. So the reason why this is being recorded is because this is intended to be then used in this program so that students can take this course, say in the spring when I'm not teaching it, right, and still be performing the work, all the homework assignments, etc., based off of these recordings. Okay, so every lecture will be recorded. So that, I guess, in terms of how I do my thing up here, that means that, one, I'm going to provide all these recorded lectures on Carmen as well. So if you miss something I said, or if you miss class altogether that day, you can go to these recordings. I will repeat all questions that, so if you ask me a question, I'm just going to repeat it so that the microphone can pick it up really well, and then I'll give the answer. And then I will not be using the Blackboard except for maybe today, because the stylus system that I'm intending to have, let's say there were some technical difficulties with IT at Scout Lab and getting that all working. So I may be using the board today and then just re-recording on my own time there. But in general, I'll be using a stylus up here to write anything that's handwritten. Okay. All right, so going into the details of homework. So 10% of your grade for each homework assignment. These are going to be fairly extended homework assignments. So this would be more difficult and more extended than a homework assignment you'd expect to see in an undergraduate course. And they'd be pretty thorough, but you have a decent, about 3 weeks to do each of them. Right? So I guess I recommend that you start these homework assignments early. I recommend you use office hours to come and talk to me or work with other students and get a jump on these early, because I think you'll probably have a difficult time getting them done if you start the day before. Okay, so please start early on these. Final project. So this is going to be 40% of the grade, and I'm expecting graduate student quality of work on these projects. Okay, so there are 2 track options for the final project. One is going to be the description of the physics of some sort of existing AM process. I'll talk about some existing AM processes in a little bit, and propose an experiment to perform on this. So you're not actually going to do the experiment because this class comes with no budget. But you would be proposing an experiment. This experiment has to be very well founded. We'll talk about proper experiment design for AM later on the semester. So that'd be track 1 if you choose to take that one. This is groups of 2 students. So you'd be teaming up with another student. And track 2, devise a new AM process and perform a complete analysis of assumed physics and resulting material properties. Okay, so this is intended to be a thought study, but a very thorough thought study grounded in physics, engineering principles, detailed analysis, etc. We have 2 students auditing the class. Obviously, you are not obligated in performing, in participating in this project, but if you wanted to, I have no problem with that. Right. I think that would be actually good, especially coming with a PhD already. I think you could show us everyone how it's done too, right? So in terms of graduate level of thinking about this. Class participation. So each student is required to present 1 journal article in class and participate in the discussions. So just to help everyone out with that, if I think I gave out all my copies. Does anyone have a copy of? Can I grab this copy of this paper? Okay, so this first paper from 1946. This is the very first one we're going to do. All right, so this is an oldie but a goodie. I was just at the Solid Freeform Fabrication Symposium in Austin, Texas last week, and people are still talking about this paper and how it relates to additive manufacturing. Okay, so oftentimes we'll call it the Rosenthal equation for heat transfer in powder bed fusion. Okay. So the very first one I'm going to do. So I'm going to lead the discussion on this paper, kind of to set the tone, set the expectations for what's expected when you present your paper, and then we're going to talk about I'm going to give some prompts, so we'll talk about some features. You will all be expected to read the paper before I give this presentation, and then we're going to have a discussion about it. So it's going to be more of trying to understand the details and how this a model like this can be then used to understand what's going on in powder bed fusion. So we'll be going through this paper. If you came in late and you do not have this yet, there are some going around. Everyone have this? Okay. 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 The last thing I guess I want to say that's logistics in nature is that this is the first time this course is being offered. And beyond that, there is no book for a class like this. And really, this is quite a unique class. So there's a class like this at Penn State University. And as far as I'm aware, there's no other class like this in the world. Okay. So I'll talk a lot about how there's a lot of classes on additive manufacturing technology, and there are books on additive manufacturing technology and how that's different. But a technology course in additive manufacturing, which also we have at Ohio State as well, is more of, I want a part, it has to have this surface roughness, this material strength, etc. What tools should I use to get that? And that would be selecting tools, how do you do 3D modeling, things of that nature. That's not what this course is about. This course is about the physics and engineering of additive manufacturing. So this is more along the lines of if you wanted to perform AM research, if you wanted to modify an additive manufacturing tool, and I'm not talking about modifying something small with the tool path, but completely redesign a new, say, laser system for AM tool, or if you want to completely redesign a new a basically heated nozzle for AM tool, what types of principles would you have to understand to then actually perform that work? If you wanted to redo the control systems of the AM tool, what would you have to do? So because this is a fairly new course, sorry, not fairly new, very, very new type of course, I, for one, am intending to basically put all my lectures online to kind of provide a resource for anyone who's interested in this. And because of that, too, I am looking for feedback, and I'm open for feedback. So if you have any suggestions in terms of what you think could make this class better, if there's certain content that you don't think I'm explaining well, etc., I'm all ears in terms of trying to make this a better course. Because I think it is fairly unique And so if it says it's fairly unique, it has to be done well. It can't just be, there's not like, you know, if I do bad in my undergraduate class, the students are just going to go and find a YouTube video that explains it better than me, right? So, and they'll figure it out, right? So I don't think they're, because this is so unique, you'd actually have to start going to conferences, which is not as accessible of a format, right, to understand this material. So I really want to make this course a really solid course in this field. So any suggestions you have, I am all for it. So. Okay. All right, so kind of starting the introduction to additive manufacturing. Sorry, any questions before I go any further about course logistics? Yes?
In terms of software, like what do you expect for those homework, like to solve those different equations? You know, like things like this.
MATLAB. Okay. Yeah. So I'll talk a little bit later about how this is not a computations course. Okay, so there's actually a computations for AM course being taught, I believe, this semester by Wei Zhang out of welding engineering. Okay. And so this is not, we're not using computational packages to solve PDEs here. So we're going to be looking at more simplified representations of the physics of AM and how we can solve that either by hand in PDEs or fairly simple computational tools to look at relationships in the physics of AM. So MATLAB is going to be sufficient. And in the second module, I'll show just like some simple solving of PDEs in MATLAB. Everything I do in the class that is MATLAB based, like for instance, I plot some sort of solution here, I'll be providing all the MATLAB code for that. Okay. Who has not used MATLAB before? Okay, good. Okay, so first, why is it called additive manufacturing? And this is a little bit of a history to it. So first off, the very first additive manufacturing tool was called three-dimensional printing. So this is an image from the patent of the very first additive manufacturing tool. This came out of MIT. This is now what we call binder jetting. So this is the first patent in 1989, right? So we're coming close to 30 years now for additive manufacturing. This is, we'll go through what's actually going on here. The schematic's not too clear, but the reason why it's called additive manufacturing is a bunch of people in the field got together and decided it's going to be called additive manufacturing. So there are a lot of names for this. 3D printing is actually the layman's term. So you see this in a lot of popular press. It'll be called 3D printing. So for instance, 3D printing here, 3D printed weapons, all this buzz about additive manufacturing, 3D printing. That's what it's commonly called in the news media. If you're talking to your grandmother and she has no idea what you do for research, you'll probably call it 3D printing, not additive manufacturing. But in terms of you're talking to a technical audience, it is now accepted that it's called additive manufacturing. So we use the terms additive manufacturing or AM or additive for short in this course. So I think because we're trying to train you to become researchers in this field, I think it's better just to switch your lexicon so you're talking about it in terms of how people would talk about it at an additive manufacturing conference. The one paper you have here, this is actually coming from this committee that came up with what's being called now the official terminology for additive manufacturing. So this was decided by a committee that was formed by the American Society of Testing Materials, or ASTM. So it's a process of joining materials to make objects in 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. So you'll see some synonyms that you'll see in the literature. For instance, I said I was at a conference in Austin, Texas last week called the Solid Freeform Fabrication Symposium. So freeform fabrication. So even what I'd say is probably the leading conference in the science and physics of additive manufacturing is still using an older name, just because that conference was, I think, first established in 1996, and they can't change their name anymore because then they lose branding, right? But it's now officially called additive manufacturing. Also in this source, you'll see then the 7 AM categories that are currently defined. I'm not aware of any AM tool that does not fit in these categories. I'll go through each of these categories here, but as part of being able to talk about this at a technical, within the technical community, we're going to use the terminology established by this committee here. And so that means, for instance, we're going to use powder bed fusion as opposed to direct metal laser sintering, which is the trade name that EOS has devised for their tool. Right. Okay. So each of these categories has dozens of variations, so we're not going to be able to go through every single variation of these processes. Just way too much to cover. It's a fairly diverse field. And then we're also not going to cover cold processes. And I'm saying this because the physics are, I'm going to say, not as interesting. And I say this very cautiously because I have, I think, 4 of Dr. DePino's students here who work in ultrasonic AM. So I think, given the kind of composite of the class, I may add some things with sheet lamination, which is, I think, would be interesting to a lot of the students in this class. So I may try and add some content from that field as well. But in general, we're going to be talking about the thermal processes in additive manufacturing. So these would be directed energy deposition, material extrusion, and powder bed fusion. I'll go through every single one of these in the subsequent slides so you have an idea, but these are going to be the main processes that we're going to focus on in this. And if you go to an additive manufacturing conference where people are talking about what's the latest in research, you'll see the majority of the work is in these 3 types of tools here. Okay, so I wanted to go through each of these subcategories, seven subcategories, so you have an idea of how it works. This will be really the end of additive manufacturing technology, and I'll get into more of the science and engineering. But I think it's good to know a basic idea of how each of these processes behave. The first is binder jetting. This is the very first additive manufacturing technology. That was the patent from 1989 from MIT. But the main idea here is this is a powder bed process where you have a bed of powder. At each layer, you're spreading new powder on a thin layer on top of what's already been built. You're then taking basically an inkjet head. So just like an inkjet head will put down colored ink on paper, this is now putting down essentially an adhesive on the individual particles of powder, and that causes them to fuse together, adhere together in a given 2D pattern. This piston moves down, and then you just do this over and over and over again in a cycle until it's complete. So here's a video showing this. Volume. I don't know if we have volume in this room or not. Okay, apparently we do not. So I'll talk over this. Okay, let me back up again. Okay, so here's an example of the X1 system. This is an industrial binder jet printing process. Okay, so what you're seeing here is you can see the glue or adhesive being put down on the powder. Okay, then they UV cure at every layer. And then they put a new layer of powder there. So you saw how it looked like it was erased. It wasn't erased. It was just a very thin layer of powder was put over top of it, so you can't see what was done. This is getting kind of the details of cleaning heads, all the other stuff. That's too important. But the main cycle is thin layer of powder, adhere at a certain pattern, new layer of powder over and over again until you build up a 3-dimensional part. What's interesting about this process is when you make this, you get this. Basically, you get a matrix of the powder itself and also the binder. And if you do this correctly, you can then burn out that binder or that adhesive, and it gives you this green body, which is shown here. Let me get. Oops. You get this green body here, and then what you can do from there is that this is basically just made of plaster, so it's pretty weak. You can then just put metal next to it and heat up that metal, and because this is a porous network, it via capillary action, it'll just suck up the metal into the part. And so then you can create metal parts from basically this green body mold here. So you can make really strong parts from this. So here's an example of a green body that's then turned into a metal-infused and infiltrated part that they can then use for injection molding. Right? So there are ways in which you can turn this into more durable parts, even though it first started out as basically plaster, which is very weak. Plaster and glue. Directed energy deposition. So this is one of the processes we'll be talking about a lot because it has some really interesting heat transfer problems associated with it. So this is, again, a powder process, but you don't have a powder bed anymore. What you have, the laser pointer is really small. Let me, oh, there we go. Okay. So what you have here is you have this head and you have a substrate. So substrate is going to be usually just a really, really thick piece of metal of the same, essentially the same type as the metal you're trying to print. And then what you're doing is you're blowing powdered metal through these nozzles. And you're doing a pretty high rate of speed. So you have a powder jet here, a powder jet here, and then you have a laser, or sometimes some processes use electron beams or other forms of this as well, where then you have a laser coming through the middle here, and where the jets of powder and the laser meet, that then fuses the powder at that location. Right? So it melts the powder, and then once the laser is removed, then it resolidifies, and now you have this, essentially you build up the part by making a bunch of these lines of these beads of metal powder. So here's an example of the metal substrate. You have then the powder, which is then formed here. And then also you can see that what's called the heat affected zone, this is what saw basically the laser power, is melted and therefore forever changed directly under here. So you actually see that the change in metal structure went into the base substrate here as well. So here's this video showing how this would work. So for some reason it's a little choppy. I don't know why it's a little choppy. But this is a very sped up video. It goes much slower than this. I don't know why this is choppy, but it is. So this would be making the wall of this in a layer by layer fashion, where here they're just basically blowing this metal powder, very small amounts of metal powder. You don't see it accumulating, it blows right off. And then most of it gets directly melted, and then you have this laser here. And here they have this nice multi-axis system here, so they're going to start to turn this into a cone in a second. So you can see that's an hours there, right? So 5 hours, 6 hours. This takes a pretty long period of time. It was significantly sped up. But that's the way you can make. This is a radially concentric, or actually symmetric part. So you don't have to have actually symmetric parts. You can actually have pretty much free-form fabrication. Okay, so that's one example. This one right here, this was actually printed. Basically, you just think of a welder. You can same process or same category, but fundamentally different way of doing it is that they have. You can think of just a welder, and you can turn a welder into additive manufacturing tool as well. This is a plasma welder actually. This is a company that's from Norway, but they just I forget how many $1 million facility they just built in New York State. And they're basically trying to corner the market on aerospace structural supply. Okay, so the aerospace market is dominated by titanium for good reason. It's a very strong, lightweight material, but titanium is very, very expensive. So if we look at traditional ways of which titanium would be manufactured, you take very large billets of titanium and you would mill out the part you want, which then you're basically putting a ton of titanium chips on the floor, which is all very expensive. You have to remelt that to then make something again. So what this group called North Titanium is doing is they take now rods of titanium and then they use plasma welding to then plasma weld this in what's called the near net shape of the part. So here's what it looks like when it comes off the AM tool, or the directed energy deposition tool. And then from there, they can then machine this into the the part with a nice surface finish. Okay, so instead of putting an entire rectangular billet on the floor in terms of chips of titanium, you are now just milling a little bit of this off. Okay, so if you look at titanium, I don't know what titanium costs per kilogram. It's quite expensive. That's a huge cost savings for the aerospace industry when they want to make titanium parts. Yes?
Can you use multiple nozzle heads for multi-material design? Like, can you mix them?
So I have seen this.
Okay.
Yeah, and so now the problem then becomes with material compatibility. Right, so there are some materials, some metals you just can't fuse to each other, really. So I've seen this in a few cases where they have compatible metals. Yeah. So the ultrasonic group out of DePino's lab is one of the rare exceptions, and maybe their group can talk about this a little better than I can, but the one advantage of ultrasonic additive manufacturing is you can start to merge materials that typically are not weldable. They can't weld them together, so they can do that because they're creating actually a physical interface and not melting it at the interface. When you start to melt materials, that's when you have compatibility issues. So I don't know if Norsk Titanium is doing this because they are focused on aerospace, and aerospace is a lot of titanium. But people have shown some multi-material fabrication. Okay, so that's the DED category. We will talk about this process quite a bit. It has some really interesting heat transfer problems that we can look at for this process. Material extrusion, this is what you call what more commonly called as maker bots, right? So I'm sure everyone has seen these before. So the main idea here is that you have your feedstock, which is in filament form. These are usually thermoplastics, ABS, nylon, you name it. There are tons and tons of materials that have been used with maker bots. And then you're feeding this through this heated head. Oftentimes this moves in the XY direction, then your table moves in the Z direction. And you can then print things with this. So here's an example. This is, again, an accelerated video of fused deposition, which Stratasys calls fused deposition modeling. So Stratasys is the company who first brought material extrusion onto the market. They are by far the industry leader. They're out of Minnesota. But here's an example of printing of what the nice advantage of this is you can make some really large structures pretty easily. It's very robust. So that's a fairly large structure that was made. Okay. This is something I've worked on quite a bit. So that was the product from Stratasys is a thermally driven process. They're melting the polymer. Then the act of solidification is what makes it into a rigid structure. There are ways in which you can do this all at room temperature. So here's an example of work that I did in my graduate work. Material extrusion all at room temperature. So here we are printing ceramic paste, and so there are ways in which you can the thermal process. Stratasys process works by a phase transition. So your material rigidifies by the act of solidification. So you can use materials that are what are called yield-through plastic, and that just means that they're shear thinning. So the material, when it's going through the nozzle, actually becomes less viscous, and that's because the shear stress causes fibers in this to align, and therefore becomes less viscous. And then once it leaves the nozzle, that shear is removed and all it then sets up. So you can build three-dimensional structures if you have the rheology right. So this is something we're looking at for biomaterials. This has also been used for other applications. So here's an example of again, choppy video, I don't know why, but this is printing of antennas on three-dimensional structures. So most all antennas, at least microfabricated antennas, are planar. So these are made by basically etching processes on flat substrates. This is one of the first examples that was ever seen where they can start to print this on curved surfaces. They can have different performances for your antennas. So this is another example of this. Okay, material jetting. So this is, for those of you who have ever seen the polyjet processes that came from Objet, the main idea is this works just like an inkjet printer, except that the inkjet you're printing now has, basically occupies more volume. So you can start to print in the third dimension. So the idea here is you have all these inkjet heads. What's nice about this is you can start to print in colors here, and you print at each layer where you want it to go. You use a UV lamp to then cure it in place, and then you use this leveling roller to then make sure that this surface is always flat. So this is a polyjet here from Objet, which then was purchased by, I forget who these got bought, who this company got bought by. Again, I don't know why these videos are all choppy. It's quite annoying. Okay. So here you can see a little bit better, but this is that each layer is then putting a very thin layer of polymer down to build up a three-dimensional structure. Here. So you can see that it has, I'll replay that. Hopefully it's less choppy. So after it's cured, you can see, well, the one on the right, let me go back. Okay, the one on the right, go away. The one on the right has all the support material still on it, and here's after you remove the support material, showing them the edges of the part. This has been used for electronics now, so this is Fujifilm Dymatics, which is, actually I just visited Fujifilm on Friday last week in San Jose. So they make electronics with the additive manufacturing modality. Basically, they do print electronics. So you can now print dielectric materials, metallic structures. They were doing magnetic structures. So they're actually looking at printing. How do you print magnetic tape for data storage using additive manufacturing? So a lot of cool things that are still coming out in terms of this is brand new things that Fujifilm is doing and other companies are doing with printed electronics for using additive manufacturing. Oh my God. This is fun. These recorded videos are going to be terrible, right? Okay. So the GE Aviation, Brian, you probably are very familiar with this part at the bottom left here. So this is particle fusion. We'll actually spend the most amount of time in this class talking about this process. It's arguably one of the most commercially viable processes for durable goods. So GE bought up 2 of these companies within the last 2 years, right? Was it 2 years ago about? They built up the two companies. The vast majority, before GE bought these companies, the vast majority of the activity in powder bed fusion was happening in Germany. Because the Germans are really good with laser optics, really good with powdered metals, but they were basically dominating this. I think all the headquarters of these companies are still in Germany, but GE owns them now. There are a few competitors that are still in Germany, and then also 3D Systems in South Carolina bought up one of their competitors as well. But the main idea behind powder bed fusion, I'll show you this in a second, is you have, just like some of the other processes, you have a layer of powdered metal. Also, you can do powdered polymers as well, which is often called selective laser sintering. But powder bed fusion usually is powdered metal, and then when you're doing it every layer, you're running a laser over a 2D pattern, so then selectively melt that powder in a specific pattern. You then recoat that top layer with more metal powder, and you do it over and over and over again until you get the part you want. So we'll start this at... Okay, so here's an example of this process. So you can see the metal powder, when the laser hits it, it changes basically its reflectivity, right? So you can see it's turned from this kind of rough powdered surface into fairly smooth metal. So I think there'll be more videos in a second. Maybe not. Here, we'll go through this again. So you can see the laser hitting the powder, turning into solid metal, then a recoater blade comes across, and then puts more metal powder down, and does this over and over again. So GE has invested in a very large way into this. This is probably the most famous AM printed part by GE. So what was, I guess, illuminating about this part is this was a fuel nozzle in one of their aircraft engines. And before, this had to be made from 20 individual parts that were then brazed together. So why it had to be made from 20 individual parts is that inside this fuel nozzle, there are a bunch of, basically, I don't know what's inside it because they haven't told anyone, but I've heard that there are a bunch of tortuous channels. And so this creates a certain flow patterns, which is then good for aerosolizing the jet fuel. And so to make this before, they'd have to basically braze together a bunch of little pieces, which is a very expensive manufacturing process. And so what they were able to do with powder bed fusion, because you get a lot of this complexity more easily with powder bed fusion, they're able to make this out of a single process. So they could take what was 20 individual processes, plus then the brazing of them all together, which is very manual labor intensive. They're able to then do this in a single manufacturing process, and therefore save weight, save time, save for a variety of different things. We'll talk about that process extensively, so I'm not going over it too much. Sheet lamination, so we have some students in this class who study sheet lamination. This has been done with just paper, actually, a lot. So they look at how can you take sheets of paper or any type of material, put adhesives on them, and then glue them together in a certain stack of patterns. So if you have a bunch of 2D sheets of paper in the right orientation, you glue them all together, this actually becomes really, really rigid. So anyone who's picked up a ream of paper, it's quite heavy, it's quite rigid. Now if you glue all those pieces of paper together, it becomes a pretty durable product, actually. So that's with metal. There's a group at Ohio State, Dr. DePino's lab, which are world leaders in ultrasonic additive manufacturing. And so what's advantageous about this is you can start to look at building composite structures. So here's an example of ceramic material, then integrated with aluminum material, which is really rare. You don't see that in too many manufacturing processes. Okay, so what this does is it uses an ultrasonic horn to take very thin films or thin foils of different material feedstock, and it then essentially creates with ultrasonic energy, causes then the interfaces of these two different materials to actually mechanically interlock, and now you can create composite structures, which is very unique. You don't see this too often. Right? You can then also have a machining head on this. I don't know if this specific tool has a machining head on it. You can have a machining head and then machine away regions that you don't want, so you can make more complex structures, because If you don't do that, you have pretty much just planar structures. But oh, here you go. Here it's milling away stuff that you don't want here. But then you can go and repeat the process and get these composite materials, which are very high value added material. Okay, last one. VAT photopolymerization. So this is an old one that you've probably seen before. And if you've seen Carbon 3D, which is the hot new company in additive manufacturing, this would be their process, or one that they've modified. They didn't originally conceive of this process. But the idea here is that you have a vat of what's called a photopolymer. So photopolymer is a polymeric material that when you expose it to UV light, will solidify. Usually UV light and temperature. And so what you can do is you have a platform here. At every layer, what you're doing is you're selectively exposing that top layer to UV light that causes a photochemical reaction, which then cures that material, and then you drop this platform. You make sure that this vat is at the same level, and you can make parts in a layer-by-layer fashion. So here's another video of this in action. So here is, you can see a laser exposure in the UV of this vat of material. It's mostly clear, so you can actually see the bed underneath this. You can see that kind of corrugated surface of this bed, but they're then exposing every layer. And here it is, multiple layers up, right? So everywhere around, it's tough to see because it's clear, is this photopolymer in this region. You can only see it when it becomes solidified. This is another success story, too, in terms of additive manufacturing. So Invisalign braces, which you've probably seen these commercials on television. Maybe one of you have had Invisalign braces at one time in your life. So you raise your hand? Oh, okay. Okay. What they do is they actually make the mold for these Invisalign braces. So one of the advantages of additive manufacturing is you can create custom products pretty easily. So they can, just by changing the 3D file that makes this, they can make a mold in the shape of your teeth as opposed to your neighbor's teeth, right? And then they can continually change this mold over the course of the treatment with your braces, so that they can change how your teeth are in your mouth. And so they've used this to create the patient-specific mold, and then they thermoform plastic sheets over this so it has a nice smooth surface. So this has been another success story of additive manufacturing. This is used to make, I don't know how many thousands of Invisalign braces per year. Okay, so we have, okay, so in general, I'm going to take a break sometime in the middle class, but today I just kind of blew through the break. So the break will be somewhere around 5 minutes or so. So I'll just end at 10:15 today as opposed to take a break because we're almost done. Some additive manufacturing advantages. One is complexity for free. So this is what I was talking about before. This is the GE example, where you can make this part that used to be 20 parts that were brazed together. You can do this in a single manufacturing process. This is an example. This is something that we built in my lab. This is a synthetic scaffold that was tailored to CT scans from the CT scans of the skeleton. Right, so you can get fairly complex structures. And not only was it tailored to the CT scan of the skeleton, we also had different materials in different regions. So you can see this is an X-ray of what we made. You can see parts of this attenuated the X-rays a lot, and parts of it did not attenuate the X-rays a lot. So the reasons why we did that are beyond the scope of this class, but we can start to add multiple materials into single constructs. Custom solutions for custom needs. This is an example of a custom brace. This is actually for an animal. This is a dog in which they did this surgery for, but they custom made this titanium plate for the specific dog. The Invisalign example will be custom solution for custom need. And then the other reason why AM is quite powerful is because it bends the cost curve. So I don't know how well you can read this there, but injection molding would be a very common way in which you make plastic parts. Right? So if you want to get your production plant going for injection molding, you're talking around somewhere around $100,000 to build your core and cavity set to just produce one part. And so around $100,000 and $10,000 to produce this core cavity. And then of course, the more parts you produce, your cost per part goes down with injection molding, right? So when you get somewhere in the order of 1,000 parts, it becomes quite cost competitive with injection molding. What AM does is allows you to continually change the shape of what you're making, given the ability is the idea of being free form, and we can say move the laser anywhere we want, but we have a lot of options in where we move the laser, where we put the polymer down. And so therefore, making a bunch of parts is not that much easier than just making one part. And so this cost curve is fairly flat for AM. And so this makes it very valuable for cases in which you have very, very low production numbers. All right, so you see that the intersection of injection molding and some of these SLS, that's powder bed fusion for polymers. FFF is material extrusion. These are just, I took this from this paper. They weren't using the ASTM agreed upon terminology. But you can see that this cost curve doesn't intersect until you get to around 100 or 1,000 parts. And then some of the more traditional manufacturing processes can be more cost competitive. And so why this is valuable is that this makes this a very valuable process for the high value, low volume manufacturing production that you see primarily in the medical and dental fields and also aerospace. And that's why I say GE has invested so heavily in these processes, because they have a product line that has, it's an extremely expensive product line, and they don't make all that many aircraft engines, right? Compared to the automotive industry, which is producing about a car a minute at one of their factories. How many aircraft engines does GE make a year?
I don't know for total, but it's much less than automobiles, more than 100,000.
Tens of thousands a year, right? Yeah. Okay. So even though, say for instance, if you're doing injection molding of interior parts in a car, that's high value manufacturing, and you're never going to go away from injection molding, because you can make a new part, you can push out a new part about every 5 seconds. You can never do that with additive, but what you can do is you can make the core and cavity for the injection mold, right? Because you're only making a few of these cores and cavities. That's low volume production. These are actually fairly complex parts. They have, I don't know if anyone has seen injection molding before, but they have a lot of moving parts in them. They have internal cooling channels in them. They're really complex pieces, and they cost around $100,000 to make one of these. Okay, and so you can, automotive industry can now make their cores and cavities, and then now use them in a traditional injection molding machine. Yes?
Do you think the incorporation of fiber composites for like lightweighting in automotive is
Yeah, because those use molds as well, right? Yeah, potentially. Yeah. I don't know. Yeah, but I would think so. because you have to mold all those parts around metal structures usually. Yeah, or even plastic structures too if it's strong enough. So here's an example of injection molding, and then the interesting thing too, and we won't talk about this too much, is with traditional manufacturing, if you want to build in cooling channels, you drill those cooling channels, so you can pretty much only do straight channels. With additive manufacturing, you can now have what are called conformal cooling channels. So with a straight channel, you can't get your straight lines all that close to the surface. With conformal cooling channels, you can make those lines very, very close to the surface, so you can cool or solidify your plastic much faster now. So you can reduce your cycle time on this. Here's an example, sheet metal forming dies produced by additive manufacturing. Again, sheet forming is really, really inexpensive. The molds for this are very expensive, right? So you can convert some of the manufacturing workflow from that to be less expensive with additive manufacturing as well. These are where people are saying that the automotive industry, which is a huge, huge industry in the United States, could see some benefit of this. You're gonna be kidding me. Okay, I didn't figure out, I don't know if it's because I'm recording this that PowerPoint doesn't seem to work too well, but practicing recording this at home when you only practice for 5 minutes to make sure it records is not apparently enough to figure out if it's going to work for a whole class. All right. Okay, major areas of AM research. There are a lot. We do not have the ability to go through all of them in this class. The ones that we're going to focus on are energy transfers, that would be heat and fluid transfer, mechatronic integration, that's the integration of all the different subsystems in an AM tool, and solid mechanics. We will get into a little bit of metallurgy, crystallography, but honestly, that's such a complex subject that if you're really interested in that, you should probably take a metallurgy class out of the material science department, if that's something that would be valuable to your research. Also, I want to note that there are other classes at Ohio State that are covering some of these other topics. So Wei Zhang in welding is teaching a class on computational methods for additive manufacturing, I believe this semester. So if you're interested in that class, that's an option. Applications, David Dean out of actually plastic surgery at Ohio State is teaching a class on additive manufacturing for biomedical applications. And then in 1 year from now, Alok Sutradhar out of mechanical engineering is going to be teaching a class in additive manufacturing design. So there are other classes that cover more of this entire scope of additive manufacturing research. For those of you who are doing additive manufacturing research, I think you should be aware of what type of venues there are for publishing your work. So Solid Freeform Fabrication Symposium is a very popular one, Materials Research Society meetings, and also ASME and Society of Manufacturing Engineers has conferences every year, which have a lot of additive manufacturing symposia, or like, for instance, this one is entirely about additive manufacturing. 3 days of as many additive manufacturing talks as you could possibly see. Journals, some of the common ones, and then also there are AM trade shows too as well. So I don't know if anyone has ever heard of Rapid. This is the big additive manufacturing trade show every year. I've been to AMUG before, which is kind of fun. It's just all the tool manufacturers come in and they have these really, really elaborate booths, and they show off all their tools, and they print things in front of you, and they give away free food and drink and all that stuff. It's fun. So, so there are, I guess, venues to learn more about this. As I said before, this class is about additive manufacturing science and engineering, not additive manufacturing technology. So the analogy I like to use is if you want to learn about car technology, you go and read Car and Driver that you pick up at your local CS. But if you really want to know about the fundamentals of how a car works, and say you want to work in the combustion part of Ford, you should probably read a textbook on internal engine combustion, because you're not going to learn that in a magazine, right? So same thing here. AM technology would be, what are the strengths of your different materials that you print using material extrusion, and so therefore you know what material you should pick. What we're talking about here is some of the fundamental AM science and engineering of additive manufacturing. So if you want to do research on the process, if you want to build a new tool, if you want to modify a tool, you have the knowledge to do so. That's going to be the focus of this class. So if you're really interested in AM technology, there actually is an AM introduction to AM class that's being taught at welding engineering this semester. So for those of you who are still kind of exploring what classes you want to take this fall, if you want to take an AM technology class, that is offered. But this class will not be it. This will actually be the last time we really talk about, the slides I just showed will be really the last time I talk about AM technology. We'll be talking about what's happening at the scientific, the physics and engineering of AM. Right, so just fair warning to everyone. That means solving ODEs, that means solving PDEs, that means looking at principles of heat transfer, fluid mechanics, etc. Very different topic than AM technology. Following along those lines, there are quite a few AM technology textbooks. And I either purchased these or got all of them, seeing if they could help this class. None of them will be of any value to this class. So you can, some of these are available on the library, either via download. Some of them you can just get online, actually. They're all AM technology textbooks. There is not really a good textbook for this class. Ideally, after I teach this class for a few years, and get some feedback from students, it may turn into a textbook. That'd be the ideal, I guess, end destination for this class, is actually having a textbook that is built from what I do and the feedback from students. But right now it doesn't exist. So we're going to be going through some of the, I guess, fundamental papers on that. One of the things we're going to be going through, this is essentially a textbook, but it's not a textbook. This is like a 120-page overview of additive manufacturing engineering, which we're not going to read the whole document. You're going to read part of it. But there are some sources that are, I guess, becoming more textbook-like that are valuable for this type of topic matter. There's not a textbook right now. All right, and then last thing I want to mention, I believe this is the last thing, yep. Last thing is that there is, there are kind of two ways to look at the physics of additive manufacturing. There's one that's the computational methods. That's using, say, for instance, ANSYS, Abacus, or custom-written computational tools to try and understand what's going on, for instance, at the melt pool. This is at the very area, the region where the laser hits metal powder and powder bed fusion. You can look at computational methods to try and understand what's going on, and also a lot of people look at scaling laws to understand, basically, as you increase laser power, as you increase the spread of the laser energy, how that affects, say, the melt pool dynamics. We're going to be looking more at we're going to favor scaling laws so we can understand what are the relationships between your different process inputs and your outputs, as opposed to computational methods. So computational methods are being taught out of welding engineering. So, and that's an entirely different way of looking at the problem. You have to consider a lot of aspects in terms of mesh size, all these other things you care about in computations. We're not going to be talking about that here. We're going to be looking at simplified descriptions of the physics so we can understand how process parameters affect process outputs in this. All right, with that, I went over the time I said I was going to, but on Thursday we'll start getting into basically a review of ordinary differential equations and partial differential equations, specifically ones that will be valuable in this class. Any questions you may have about class A? Maybe.
Those journal articles, how much